Hey, welcome. Today we're diving into some really cool new research that gets at one of the biggest questions out there. Are the ingredients for life, the basic building blocks, super rare, or are they basically everywhere? Let's get into it.
When you think about it, the whole search for life out there, it all comes down to this one simple question. Are we on some wild goose chase for a cosmic needle in a haystack? Or is the universe just full of the stuff needed to make life?
It's kind of like baking a cake. You can have all the right ingredients, the flour, the sugar, the eggs, but if you don't have an oven set to the right temperature, you're not getting a cake. It's the same thing out there in the cosmos. We're looking for planets that have both the chemical starter kit and that perfect cosmic oven to get things going.
Okay, so let's start there. What exactly are we looking for when we talk about these ingredients for life? All right, meet our star player, hydrogen cyanide. Yeah, HCN. And I know what you're thinking, cyanide, right? But hang on. In the world of prebiotic chemistry, this molecule isn't the bad guy, it's the hero. It's this incredibly versatile building block, almost like a chemical Swiss Army knife. It's crucial for forming the absolute foundations of biology, things like amino acids and even parts of RNA. And of course, every great recipe needs a place to cook. For the origin of life, one of the top theories is the warm little pond hypothesis. Just picture it. These shallow pools of water on a really early, volcanic Earth. They'd fill up, then evaporate, then fill up again. And that cycle is just perfect because every time the water evaporates, it concentrates all those important molecules like HCN, cramming them together and making it way more likely they'll react and build something new.
Okay, so we've got our key ingredient, HCN, and we've got our kitchen, the warm little pond. So, how do we get the groceries to the kitchen? And this is really the heart of the matter. If life is going to be common out there, then this stuff, this HCN, has to be easy to get. So where does it come from? How does a brand new planet get its first batch?
Well, scientists have basically two main ideas here. First, there's what they call exogenous delivery. Think of it like cosmic Uber Eats. Comets and meteorites crash land, delivering HCN from space. Option 2 is endogenous production, which is more like a home-cooked meal. The planet makes its own HCN right there in its atmosphere, using energy from lightning or its star's UV light. So the big question is, which one is the main source? And that's exactly where this new research comes in. A team of scientists decided to really test this second idea. They started treating planetary atmospheres like these giant cosmic chemical factories, and they built some seriously impressive computer models to see just how much HCN these factories could churn out.
So here's what they did. First, they built a baseline model of Earth's atmosphere from way back, about 4 billion years ago, right when life was getting going. Then, they just started tweaking everything. What if the star was a different type? What if the orbit was different? They ran almost 3,000 different simulations, changing all these variables. And then, and this is the most important part, they calculated how much of that brand new HCN would actually rain out of the sky and get down to the surface, where those warm little ponds would be waiting. So after running thousands of these simulations, what was the verdict? Is getting enough HCN really the big bottleneck that stops life from starting all over the place? Well, the answer was a huge no. It turns out that in roughly 68% of their simulations, these planets could make more HCN in their own atmosphere than what they'd get from even the most optimistic estimates of meteorite deliveries. Just let that sink in. Most of these worlds were way better at home cooking the stuff than waiting for a delivery. And this chart here really drives the point home. You can just see how much more productive those atmospheric factories are compared to waiting for meteorites. The bottom line is, a planet that makes its own supply is way more efficient. It suggests that HCN isn't some rare exotic ingredient. It might just be a standard feature for a whole lot of rocky planets. And the researchers who did the study, they summed it up perfectly. They basically argue that the availability of HCN, well, it's just not the rate-limiting step for life to get started. In other words, getting the ingredients probably isn't the hard part. So what are the ideal conditions for one of these HCN factories? Well, the study found a few sweet spots. It turns out planets around stars like our own sun are great candidates, especially if they're on the colder outer edge of that just right habitable zone. And here's a big one. You need a good amount of methane in the air. Anything over 500 parts per million really seem to kick production into high gear. Also, atmospheres with more carbon than oxygen, what chemists call a reducing atmosphere, we're way better at this.
But here's where it gets really interesting. Yeah, planets like Earth are good candidates, but the models found a surprise hotspot. planets orbiting super close to small, cool M-dwarf stars. They could also be incredible HCN factories, and that is a huge deal because M-dwarfs are, by far, the most common type of star in our galaxy. This just blew the doors wide open on where we could find these vital ingredients.
Okay, so let's zoom out. We have all these fascinating results. What does it all mean for the big picture, for our search for life out there?
Really, the biggest takeaway is this. If the ingredients aren't the hard part of the recipe, then the odds of life getting started somewhere else just got a whole lot better. It means the real bottleneck, the truly difficult step, probably isn't the chemistry. It's something else.
Let's just look at these numbers again because they're pretty wild. So you see that 68% of their models made more HCN than meteorites could deliver? Okay, impressive. But get this. A full 41% of them made even more HCN than we think early Earth had. That's just wow. It means there could be planets out there that are even more primed for life, chemically speaking, than our own home was.
Now, of course, these are all computer models, right? They're incredibly sophisticated, but they're still simulations. So how do we know if they're right? Well, there's only one way to find out. We have to actually look. And the incredible part is we are right on the verge of being able to do exactly that. Say hello to the Extremely Large Telescope, the ELT. It's coming online in the mid-2020s, and it is an absolute game changer. We're talking about a 39-meter mirror. It's going to be the largest optical telescope on Earth, period. And one of its key instruments, called METIS, is designed for one specific incredible job: to sniff the atmospheres of distant exoplanets and tell us what's in them, including, you guessed it, molecules like HCN.
And that really brings us to the final big question. This research makes a powerful case that the chemical ingredients for life, they aren't the rare part. They might be common as dust. And if that's true, it shifts the entire conversation, right? It forces us to ask something maybe even more profound. If the ingredients are everywhere, then what's the truly rare spark? What's the secret sauce that actually gets life started?